we're going to estimate how high we can jump on the moon. This is basically the high school physics. Let's set the parameter here. Okay, now the muscle has a lift power. Okay, that's 160 kilogram. You can lift 160 kilogram. Well, newtons, you have to multiply G. It's like 352 pounds. If you are 80 kilogram, about 176 pound, then this means you are able to lift one same size person yourself. Okay, so that's reasonable assumption, because I think it's astronaut can carry one person on the Earth. Okay, now on the moon it's get messier because you have all the gears and stuff. So we assume it's 150 kilograms, almost double weight, 330 pounds. Okay, now 160 kilogram you can lift. If you wear this on Earth, then you have only 10 kilograms difference. That means you can't even jump at all. Okay, now we use this assumption, and you know Earth, the G is about 10, Moon is about 1.6, this average 1.67, and we assume you exert the force F from the muscle minus weight, this is the resistance, during delta T. That's the average impact. Is going to determine the momentum, and this V equate to the potential energy. So we get this equation. Okay, now weight is mg on Earth. The weight prime is m prime g prime. This m prime is actually heavy because you have a lot of gears. Okay, and on Earth man jumps 30 centimeters, about 1 foot high. Then we use this equation, we get about 244 milliseconds. But on the moon everything is lighter, so muscle can exert the force for a little bit longer, say 400 milliseconds. Okay, so with this assumption we calculate the height on the moon. It's going to be about 3.9 meters. Now this match up with the result of 1.6 gravity simulator NASA made. NASA hired the PhD guys and made a 1.6 gravity simulator, and that simulators the man can jump up 4 meters, no problem. The climbing ladder is a problem. It's rather just jump up to the top of the ladder. Okay, so for the approximation, for first level approximation, this calculation works very well. Now of course we can improve our calculation. What we do is we let the astronaut jump on a scale, and we measure the profile of the force exerted, right, and time, millisecond. Now we just simply assume the average delta T and F, but in actual calculation, as you learn from high school physics, F equals ma equals m dv dt. So we have to take integral of the force over the period of time to get the momentum, and momentum is going to convert into the height. So we approximated by F delta T, the equals mv, but more accurate method is to get the muscles force profile and integrate over the time, and that's where we get the impact correctly. Impact is change of momentum. Okay, and one more thing we have to consider is actual gravity. We assume average 1/6, but the far side is higher density, and probably center of gravity is on the far side, and near side, what's happened is the gravity is a function of the distance from the center of gravity. So far side is going to be heavier, higher gravity. Near side, the face we can see, the moon, has a lower gravity, so that's going to probably increase the jumping distance. So, but we don't have this data until we send some probe and measures actual gravity on the far side and near side. But we know the average is 1/6. This is just simply average. Like moon, the weight distribution there is very skewed. It may be, gravity may be different depending on where you are standing. Okay, so that's another area we can improve the model. So overall, the somewhere around 3.94 meters, that's a kind of the distance height we can expect if astronauts jump on the moon. Okay, now we have other video talking about the distribution of this gravity and stuff. Please check it out. Thank you.